In this lesson, we're going to start our new unit, which is going to deal with continuous probability distribution models. So before we start the new stuff, we got to review the old stuff. In our last thing, we talked about discrete things. Those are things we can count. Here, we're going to look at things we can measure. Now, counting was kind of nice because we could actually make a list of all the different possible outcomes and then find their probabilities. That's how we made our charts, right? So for example, if I want to find the probability of rolling a sum less than 9 with a pair of dice, I could make a list of, well, what could I get? I could get a sum of 2. What's the probability of doing that? Well, the only way I can get 2 is a 1 and a 1, so 1 out of 36. Or I could get a 3. How could I do that? A 2 and a 1 or a 1 and a 2. So 2 out of 36, and so on and so on and so on. I can actually make a list of these things. Totally doable. It might take some time. It might not be nice numbers, but I could do that. Unfortunately, when we deal with continuous things, things that we measure, we can't do this anymore. There's always going to be an infinite number of possibilities that a variable could fall into. So for example, what's the probability that a student will have a height less than 150? What heights could they have? Well, sure, they could have 150. Sorry, we're saying less than 150. They could be 149. That's totally doable. But what about 149.5? That's another choice. How about 149.55? That's another choice. Or 555 or 555 or so on and so on and so on and so on. That's just looking at one number and some decimals to it. As I said, there's going to be an infinite number of possibilities. We can't make a list. Not possible. So we're going to have to approach this in a different way. And a different way is we're going to make graphs. If we go back to when we first started talking about data, when we did continuous data, we often made ourselves an interval table. And then we looked at their frequencies, and we may say, oh, between 0 and, I don't know, 10. And then we go from 10 up to 20, and so on and so on and so on. And we'd say there might be, I don't know, 1, then 2, 3, then 5, and so on. Well, if we do that, make our graph, and then we put our smooth curve over it, we learned about some different possible outcomes. For example, the one here, this would look like a symmetrical thing, right? Now, we're going to have to deal with that situation when we examine probability this time. We're going to look at these graphs. So let's think with these graphs for a second. The nicest possible graph, actually, hang on, I'll go back 1 second. So let's talk about that graph. So there's going to be a variety of continuous graphs. We'll start with kind of what I consider the standard one, a symmetrical graph. We call this the normal curve, and we'll spend more time with that later on in this unit. Okay. The nice thing about this curve and every other continuous curve is if you examine the probabilities, these are all the different possible things that could happen. I could have something that is that big, and then that big, and that big, and that big, and that big, and so on. This graph will include every single possible thing. In other words, it has 100% of the outcomes. It's like my table, the big list of things, but it's a graph of all the different possible things. So, if I can figure out how much of this graph is involved in the situation that I want, maybe I want to know all the people who are between here and here, and I can figure out for myself, oh, that's a quarter of the graph. Well, so if it's a quarter of all the possible outcomes, that means it's 25% likely. That's the probability. Okay. So our big idea for this unit is to try and find the area underneath a curve. Now, there's a variety of curves that we can have, and we can have our negative skew or our positive skew. We can have something that's bimodal. It's got one mode, two modes. We can have exponential curves. And we can have a variety of situations, but they all have the same idea. If I can figure out how much of my graph is included here, oh, that's 3/4. Well, then the likelihood is 75%. Or, hey, this is only a small bit over here. That's 1% of the curve. Well, I figured out the probability then. Today we're going to start with the easy one, the one that hopefully we can all draw and will make the most sense to us. Okay. We're going to start off with the uniform distribution. Uniform, like we learned previously, means that everything is equally as likely to occur. In this case, the curve is actually a straight line. What does that mean? Let's take a look at an example. The driving time from Thunder Bay to Winnipeg ranges uniformly, there's my key word, between 480 minutes and 540 minutes. In other words, each of the times in between are equally likely. So let's make a graph. What would a graph look like here? Because I can't list all the possibilities, I'm going to graph them instead. What are the different times? That's what X stands for. Well, it said the lowest I could have is 480. The highest I could have is 540. Now, I think of this as like a broken graph, right? There's some stuff missing at the beginning. I'm just cheating and showing the parts. And the other part of this is my probability. What's the likelihood of each of these happening? Well, 480 happens one time. 481 happens one time. 482 happens one time. How many different possible outcomes are there? Well, between 480 and 540, if I subtract them, I end up with 60 outcomes. So each of those outcomes has the same probability. They're each 1 out of 60. 480 is 1 out of 60. 481, 5 out of 60. 482 is 5 out of 1 out of 60. And so on and so on and so on. So we end up with a graph that kind of looks like this. In other words, a rectangle. Every uniform distribution for something that's continuous will be a rectangle. They're all equally likely. Okay, figure out the range of outcomes you could have, and then each of them is 1 out of that. Okay, part B, what's the probability that drive will take less than 500 minutes? So I'm hoping you guys will get 500 be somewhere around there. I want to know the likelihood that the time falls in between 480 and 500. In other words, I want to know this proportion of the graph. How much of the graph is included there? So the way I'm going to show this, I want to be less than 500. And to find that, I'm going to find the area under the curve. Now, if I look at this shape, it kind of looks like a rectangle to me. And we know that areas of rectangles are length times width. Well, how long is the rectangle? How far is it from 480 to 500? I think that's 20. How wide is the rectangle? That's this distance, which we said was 1 out of 60. So the probability, there's 20 different outcomes, each of which is 1 out of 60 chance, gives me 20 out of 60, or 2/6, or 1/3, or 33.3%. That's the likelihood that my drive time will be less than 500 minutes. What about at least 530 minutes? And my diagram, 530 would be about there. I want that section. At least 530, so I'm saying greater than 530. I got a rectangle again, and I know that there are 10 different outcomes, each of which has a 160% chance. So I get 10 out of 60, or if you will, 1/6, or 0.16666. That's a uniform distribution. Everything's equally likely. I just got to figure out what are the different possibilities and how many of them have I included. All right, you guys are going to try one. Pause it, try it, see if you can figure it out. If not, come back to the video. The lifespan of a great white shark varies uniformly from 15 to 32 years. What's the probability that a shark will live to exactly 30? Okay, so think about my shark. They go from 15 to 32, 32, each of which is equally likely, because it said the word uniform. I've got 17 different options. And I want to know the likelihood it comes out to exactly 30 years. Well, that's 1 of the 17 chances. Wasn't that my probability? 1 out of 17. All right, how about we'll die after 20 years? In other words, it lives to at least 20. Oh, on my graph, where's 20? 20 is about there. That means I've got 12 different choices, each of which has a 1 in 17 chance. In other words, 12 out of 17. C, probably the shark doesn't live to 25, so it dies before 25, so it lives to less than 25. 25 is about here. I've got 10 choices, each of which is 1 out of 17. What's my likelihood? 10/17. Okay. And if you want to use decimals or fractions or percents, I'm totally fine with those. The last one there is 0.588. Yeah. But the big thing here is I have to recognize some wording. That's going to come up a lot in the next unit. Uniform means equal. It means it's a rectangle, each of which is equally likely. Okay. That's it. That's our quick lesson today. Okay. Some homework you can try. If you're stuck on things, come see me. It doesn't make sense. Do try the homework. It's really helpful.